Hey everyone. So, when talking about the history of astronomy, we cannot skip over a guy named Isaac Newton. All right. Um, you'll see that I'm going to cover a little bit of physics, right? A little bit of introductory physics. And if that word gives you stress or anything, please don't worry. It's okay. I'm going to keep it as fundamental as possible, and we won't cover but say four or five terms, okay? Four or five concepts. So let's relate the laws of motion according to Newton to the laws of planetary motion from Kepler. All right. So to start, Newton was English, right? He was born on Christmas Day in 1642. Um, he, well, it was realized very early on in his life that he was quite a special prodigy, right? His mind was adept at mathematics like no one's business, right? Um, so he observed objects in motion on the surface of Earth, right, for a long time. And eventually, he, he hypothesized that, well, wouldn't those same laws that govern the motion of objects on the surface of Earth, wouldn't they still work in outer space, right? Wouldn't they still work up in the heavens? And and so he called this a connection, right? One universe, right? The prefix uni meaning one. Um, he went on to study at Cambridge and some very prestigious schools, but in 1665, um, there was a mini plague of sorts in London, right? The Great Plague of 1665. And so Newton had to quarantine himself in his countryside home. And so during those 2 years, well, he invented calculus. He refined the design of the telescope that Galileo used, and he refined Kepler's laws of planetary motion, right? He applied math to those laws and actually showed that, yes, they are true mathematically, right? So Newton supplied the theory behind Kepler's observational data, which was good. So, in order to talk about the first law, right, Newton's first law, we have to differentiate between mass and weight. So, all objects, regardless of their size, density, where they are in space, whatever, all objects have some mass. And by mass, I mean the amount of stuff, which is a very scientific term, meaning the number of protons, neutrons, electrons, right? It's nearly impossible to count those particles individually. So we have other ways of measuring an object's mass, but just for our purposes, mass is just the amount of stuff, right? Those stuff. And it will not change, right? Unless you say chop off a piece. The mass stays constant. The weight, on the other hand, depends on the object's proximity to another massive object. So you can think of a weight as the force on an object. And in astronomy, we typically talk about the gravitational force on an object. So, for example, if we have the Earth here, right, and a person standing on the Earth, not to scale, of course, this person has some mass, right? It has some mass, whatever it is. I don't know what it is. It doesn't matter. It has some unchanging mass. And now the Earth exerts a gravitational pull on that person, right? That's how they stay on the surface. And so we can say, well, there's a force, well, I'll draw it in blue, downwards, right? And that's their weight, right? So typically we measure weight in pounds, right? In science, we'll use the term or unit Newton. So let me do it in black. The units for weight is the Newton, named after, yes, you guessed it, that guy. Okay. So weight is a force that does change depending upon how close that person is to the Earth. If, for example, they walked up to a very tall mountain, they would get slightly further away from the center of Earth, and so their weight would slightly decrease. Okay, we'll see why with the equation later. Okay? All right, so the first law, you can think of this as the law of inertia. So yes, it's of motion, but it's also of inertia. Right? All objects have mass, and so inertia means that all objects have some resistance to changes in their motion. In other words, if you were to roll a ball across a tabletop, this law of motion says that it would continue to roll at that speed. But we know it doesn't. Why? Pause the video and try and think why. It comes to a stop eventually because of friction, right? The friction is the opposing force that slows it down to a stop, or it falls off the edge, and then the floor applies that force, okay? So all objects want to move at constant speeds unless a net force acts to change that speed, right? Or they can remain at rest. So if you, say, have a cup of water on a tabletop, that cup will stay there forever, right? Unless something else applies a force on it and moves it. So that's the first law. The second law of motion is basically this, right? For every force, it's comprised of some mass times an acceleration, right? And acceleration just means getting faster and faster and faster. In other words, it's speeding up. That's what acceleration means. Okay. So in these examples I have here, I have a block, right, of a certain weight, 15 newtons, and that weight is downwards, right? Why is it downwards? Well, it's resting on a tabletop, and that tabletop is resting on the surface of Earth. So the surface of Earth is down here, pulling on this block, right? So that's effectively Earth's gravitational pull on that block. That's what its weight is. But if you come along and you put your hand on top and you apply another 11 Newton force in the same direction down, well, that's 11 plus 15, that's 26, right? So we have a total force, where do I put it? We have a total force downwards. Right? And now that has to be counteracted by the tabletop, right? Unless the block would fall through the tabletop down to the ground. So thus this 26 Newton force there upwards, that's the force of the table on the block and your hand. So if we add 26 to 26, they're the same size, but in opposite directions, thus they cancel out. And so in this case, and in fact in both of the cases, the net force is 0. So thus, there is no acceleration for that block. You can do the same thing on the other side, right? On this right side. The same block, so same weight, but now you pull up, right? You attach a rope and you pull up with a magnitude of 11 newtons. So the difference between 15 and 11, now the tabletop only has to push up with 4 newtons. So thus, 11 plus, notice the 11 now is upwards, and the tabletop is 4 upwards. So 11 plus 4 is 15, equals the 15 downwards. Again, they cancel out, and acceleration is 0. So these are two cases where there is no net force. There is no leftover force, and so objects remain at rest. Exactly like what is happening to you right now, probably. If you're sitting on a couch or in a chair, you're not accelerating, right? You're stationary. But what are the two forces on you? Pause the video and try and think of both forces on you, trying to accelerate you. The two forces on you is one, your weight, that's pointing downwards towards the center of the earth, and two, the force of the chair pushing up on you. And since you're not falling into the chair or falling up to the ceiling, those forces are exactly equal and they cancel out. Thus, there's no acceleration. An example of when there is an acceleration is if you were to take, say, your pencil or an eraser or anything, a baseball, and hold it out in front of you and then release it from rest. What does it do? Right? It falls down. As it's falling, there's not really a force on it. Well, there is a force, gravity, downwards, but there's not really a force upwards. So in that case, there is a net force downwards, thus it speeds up, down, until it hits the ground, which applies a force upwards, and yada, yada, yada. So that's the second law, right? The third law of motion can be summarized as action-reaction. All right? For every action, there's an equal and opposite reaction, right? Specifically, action-reaction force pairs. For every force, there's an equal and opposite reaction force, okay? In the diagram, that space shuttle, right, the rocket boosters down there fire out their propellant downwards, and what happens to the boosters and the shuttle? It moves upwards, right? It accelerates upwards. So using the second law from the previous slide, the two forces on this rocket, let me draw it in green here. There's the, let's see, the force of the rocket down, so force rocket, and then the rocket is going upwards. Sorry about that. Force of the rocket is going upwards, right? It's propelling it down, but there is a downward force, guess what? Of gravity. Right? So these are the two force pairs, the action-reaction. Okay? Now gravity is not strong enough to hold it towards the earth, so that's why it accelerates upwards. Okay? Another example of an action-reaction force pair is, well, you sitting in that chair. What are those two forces? Your weight, in other words, the force of gravity on you downwards, and the force of the chair on you upwards. Those are the action-reaction forces. Okay? So as a fun exercise, try and think of other action-reaction force pairs, right? I guarantee you right now you can look around the room and see at least 10, right? At least 10. So just think of the example of you in the chair, okay? Excuse me. All right, so now let's see how these apply to Kepler's laws, right? But before we do that, I forgot I have a question. I don't know why the ABC and the formatting is funky, but just roll with it. How does the force that the Earth exerts on you compare with the force that you exert on it? Right? Does the Earth exert a larger force? Do you exert a larger force on Earth? Or are they equal? Right? Pause the video if you need to. Think about it. And in a second, I'll advance and see the answer. Right? All right, so it's actually C, right? This goes back to the third law. For every force, there's an equal and opposite reaction force. What this means is that, say you step down from the sidewalk, right? Or you walk down some stairs. The Earth exerts a gravitational pull on you, but that's exactly equal to the strength of the gravitational force that you exert on the Earth. Okay? It's not very intuitive at all, right? It might not make sense first time hearing this, and that's completely normal, but it's true. We'll see why very soon, okay? This is what Newton realized, right? The force of gravity between two objects only depends, well, mostly depends on the mass of those two objects. But they're equal, okay? And that's the key here. So when you step down from the sidewalk onto the street, hopefully you've looked both ways. But when you step down, you're pulling Earth up towards you, okay? So as another fun experiment, I would suggest you going outside and trying that. See if you can tell the Earth coming up at you, all right? So here is Newton's universal law of gravitation, right? We have the force of gravity, and that's equal to the constant, capital G. Don't worry about its value, just know that it's a constant of nature, times the mass 1 and mass 2, right? The product of both masses, divided by the distance between those masses squared. Okay, so what this says conceptually is that if we take two masses, m1 and m2, there's some mass. It doesn't matter what, right? Some value. And if you increase the mass of one, say we multiply this mass by 2, right? Or we add some mass to it, that will increase the strength of the gravitational pull on them both. That's what that says. So you can increase one or both of them, and you increase the force. Same thing if you were to decrease the mass. The distance comes into play where if you keep the masses constant, for example, and then if we were to push the balls further apart, right? If we increase this distance, so we move them outwards, right? That would increase the distance value, which is on the bottom of that fraction. And if we increase the number on the bottom, that makes that value or that fraction overall smaller. And so thus the force would get smaller between those masses. And this is exactly shown, or Kepler observed this directly. He didn't know why, but he observed it when he measured the orbits for the planets. The planets further away took longer to orbit. And this right here is exactly why. Okay? The mass of, say, the sun, and then the mass of that faraway planet, well, the further the planet got, the greater this distance, and the force was weaker, thus it moved slower. Okay? So we're taking several new concepts and applying them kind of at the same time to explain even more new concepts. So if you need to pause and rewind, of course, feel free. So this is an example orbit, okay? The sun is located at one of the focus points. The other is exactly symmetric on the other side, but there's nothing actually there in space. So this is a hypothetical orbit for a planet around our sun. Know that no planets have this elliptical of an orbit. This is highly elliptical. So this hypothetical planet, let's say it's right there, right, at the perihelion position, distance of closest approach to the sun. When it's right there, let me write down the force of gravity again. Force equals G mass 1 mass 2 divided by, in this case, I'll put R squared. Okay? So when it's at perihelion, the distance is minimum, right? The distance is the smallest. So this R value is the smallest it'll be. Thus, this fraction overall will be the largest it'll ever be, because the mass of the sun and planet won't change. So if the force of gravity is the strongest at this point, it's pulling that planet around at the greatest rate. Thus, it's moving the fastest. That's why this V, that's why that speed is so big. It's moving the fastest right there. And then as it goes away from the sun, right, as this r distance increases to aphelion over here, right, in this whole region, the force is getting weaker and weaker. Thus, the speed is decreasing. And at aphelion, that's the maximum distance from the sun. Thus, this r value is the biggest, and the fraction overall is the smallest. So it's traveling the slowest. And then once it passes aphelion, now the sun's gravity pulls it back towards the sun, and it's getting closer and closer, right? That r distance is getting less and less. So the strength of gravity is increasing now, and it speeds up back to perihelion. So what effectively happens is this. Let me start out here. Speeds up, speeds up, speeds up, slows down, slows down, right? This is known as a bound orbit, right? That planet, just like all planets in our solar system, are always bound to the sun, right? They don't have enough energy to ever escape on their own. And so we talk about planets in orbits around the sun as having a certain amount of energy. Okay. Now, energy, just a little bit on energy. Let's see. The kinetic energy, right? We can mention that as the energy of motion. The faster an object moves, the more kinetic energy it has. So that means that planets, when they're at perihelion, have the greatest kinetic energy because they're moving the fastest. Potential energy, on the other hand, is the energy that depends on distance, right? So actually, I'll just put distance, right? So now potential energy means that, well, if it's closer to the sun, it has less potential energy. So at this point, the total potential plus a kinetic is some amount, right? The actual value is not important. The relationship between each of these points is. So as it moves out here to now aphelion over here, the kinetic energy is minimum because it's moving much slower. Why is it moving slower? Well, it's further away. In other words, now the gravitational potential energy is maximum. So what they've effectively done is flipped. At perihelion, kinetic energy was maximum, potential energy was minimum. At aphelion, kinetic energy is minimum, potential energy is maximum. And so as this planet moves in the orbit, these values just flip, right? They increase or decrease, but the sum always remains the same for all points. And so that's why the total energy for an object in orbit does not change. Right? The type of energy just kind of flips from one to the other. It goes from there, and then it goes back, and then it goes back to there as the planet orbits year after year. Okay? There are instances of orbits changing, right? Of, well, energy being added from an external method, and that's what astronomers use when they send spacecraft to distant planets, right? So unfortunately, this link won't send me to the animation, so it's just a still picture. But if we look here, right there, on August 5th, 2011, that was the launch date for that spacecraft, the JUNO spacecraft. It launched from Earth at that position on August 5th, 2011. And so it launched, and its trajectory is here in white. It went out there, right out there like that, as Earth went around in blue, right? So the spacecraft went out. The further it got from the sun, the slower it moved, but it didn't have enough energy to fully escape and get to Jupiter out here, which is was its destination. So it was actually pulled back towards Earth and the sun. Well, by the time it got back here, Earth had already traveled around 1 year. So as it came closer and closer to Earth, it sped up and got faster and faster. Right? Thankfully, it didn't collide with Earth and just passed by close by and then went much further away. Right? And then it reached Jupiter on July 5th, 2016. Right? So almost 5 years, 71 months. So what it effectively looked like was this, right? It launched, slowed down, slowed down, slowed down, approaches Earth again, speeds up. And yes, it made those sound effects. It did. And then it reached June, almost 5 years later. So that's a way to add energy to an orbit, right? And astronomers use this for basically every time they try and send a spacecraft to a distant planet, because this is actually much more energy efficient and takes less time than trying to just send it right there, okay? Or rather, around and like that, okay? This gravitational slingshot effect is the way to go. All right, thanks for watching.